So this movie is going to look at the evidence that benzene is much better thought of with this delocalized model rather than the localized double bonds shown here. This is sometimes called a Kekulé structure. I should note that a lot of times I'll be using the Kekulé structure because it's much easier to talk about mechanisms when you start off with benzene looking like this than looking like that. But this is a much better idea of the actual bonding at work in benzene. Now, if we think first of all about what these structures would look like, both of them are going to have all angles at 120 degrees because we're all in a nice perfect hexagon here. Each of these carbon atoms is trigonal planar because each of these carbon atoms has got 3 bonding groups on it, single bond there, double bond there, and the hydrogen. Here we've got whatever bond, whatever bonding, and hydrogen there. So they're trigonal planar, 120 degrees. But if we think about bond lengths, we talked about bond lengths in a previous module. Got the carbon-carbon bond length is typically 154 picometers, carbon-carbon double bond typically 134 picometers. So if we had the localized double bond structure, this is what we would see, alternating 154 and 134 picometers. The reality of it is that all the bonds are equal and they're at 139 picometers, which points to this nice delocalized structure. In other words, there's no difference between this bond and this bond because in one of the end structures this is a single and in the other one it's a double, and where this was a single this was a double, and where this was a double this was a single. So the overall delocalized model, the average of the 2 possible localized bondings. Another one would be think about isomers. Think about 1,2-dichlorobenzene. Well, if we had the localized model, then there'd be 2 isomers, wouldn't there? There would be the isomer in which both chlorines were attached to carbons that were double bonded to each other, and there would be the isomer in which the chlorines were attached to carbons that were single bonded to each other. These would be 2 very definite molecules. On the other hand, only one isomer of 1,2-dichlorobenzene has been made, and you can see here that when we use the delocalized model, they would be the same. Okay, each chlorine is bonded to an identical carbon atom. So structural evidence, first of all, from the actual geometric parameters of the ring, the bond lengths, and then secondly, the lack of the isomers, different isomers that you would expect if you had the localized double bonds. Other evidence comes from so-called delocalization energy, and this is energy that is extra there in that ring, extra energy that's keeping the ring together, extra energy that would have to be overcome if you want to mess around with the delocalized bonding. Now, in order to think about this, let's go to a topic that we explore in the thermochemistry module, the idea that you can use bond energies to get a feel for delta H for a particular process. Now, if I think of this process here, the hydrogenation of a carbon-carbon double bond. Okay, so I've got the bond energies, carbon-carbon double bond, 614 kilojoules per mole, hydrogen-hydrogen bond there, 432, carbon-carbon single bond, 347, and carbon-hydrogen bonds, 413. Now, if I was to do this reaction here, I would have to break some bonds, and of course I'd have to make some bonds. Ones I would have to break would include the carbon-carbon double bond right there, because there's no carbon-carbon double bond over here. And I would also have to break this hydrogen-hydrogen bond because there's no hydrogen-hydrogen bond left in the products. So the total amount of energy I would need to break the bonds is 1046 kilojoules per mole of reaction. Now think about making bonds here. What have I made in the products that's not there in the reactants? Well, I have a carbon-carbon single bond in the products. I only had a carbon-carbon double bond in the reactants, which are broken. So I've had to make a carbon-carbon single bond, and I've got 2 new carbon-hydrogen bonds, each of which is 413. So add those up, and my total energy that I get back out from making bonds, 1173. So the estimate of the heat energy needed to perform this reaction is 1046, which is energy that has to be put in, minus the 1173, that's energy that comes out. So the whole thing is a exothermic process to the tune of minus 127 kilojoules per mole. So that's what you would expect on average to get out every time you hydrogenate a carbon-carbon double bond. Now let's look at some examples. Here's cyclohexene. Now if I wanted to go from cyclohexene to cyclohexane, I would have to hydrogenate one double bond. Okay, so therefore I would expect the delta H for this to be minus 127 kilojoules per mole. It's actually minus 120 kilojoules per mole. Definitely in the same ballpark, 7 kilojoules per difference. That's a sign to sort of a little bit of ring energy, okay, because you've got that ring there that's sort of straining things a little bit. Maybe when you make the bond longer, you get a little bit of energy back out, okay. So you expect minus 127, actually only get out 120. Now how about one with 2 carbon-carbon double bonds in it? Cyclohexa 1,3-diene. So if we're to do this, we're going to have to hydrogenate 2 carbon-carbon double bonds. Well, each one, you'd get out minus 127, so you'd expect twice that to minus 254. The actual value is minus 232. So again, it's about 22 kilojoules associated with it being in a ring. Okay, a little bit more because you've got double bonds. Now let's go to benzene, which of course popped up on the screen before it should have done. Okay, benzene, if we were to think of it as this localized model, well then we'd have to hydrogenate 3 carbon-carbon double bonds. So we'd expect to get back out 3 times 127, or minus 381 kilojoules per mole. What we actually get back out is minus 208 kilojoules per mole, significantly less. In other words, a large chunk of the energy that we would expect to get out, we have to put in associated with changing that delocalized bonding. Okay, now the actual accepted value is that we say 21 of that's just general ring stuff, and the actual resonance energy is 152 kilojoules per mole. In other words, you don't get out the expected amount because 152 kilojoules per mole is being used up breaking that delocalization, because of course if you're going to hydrogenate it, you have to break that delocalization. So another bit of evidence from thermodynamics for the delocalized structure instead of 3 localized double bonds is you don't get out nearly the energy you would expect when you hydrogenate those double bonds. So we've looked at structural evidence, we've looked at thermodynamic evidence. Let's actually look at reactivity evidence. I said right at the very start in that first movie that one of the problems with the Kekulé structure was that benzene doesn't behave like alkenes. Well, let's get specific with that. Now, of course, our treatment of alkenes wasn't exactly rigorous and in-depth. So I'm only going to give a couple of examples that benzene doesn't do that carbon-carbon double bonds do. But we'll start off. Here's a carbon-carbon double bond. If you react it with HBr, you get addition of HBr across that double bond, if you might remember the alkene module. Take benzene, add HBr to it, absolutely nothing happens, no reaction at all. So one of the classic alkene reactions doesn't happen for benzene. Take a double bond and add Br2 to it, bromination, and of course if you remember we brominate across the double bond, and I've drawn it because if you remember you have that cyclic bromonium cation intermediate, so one bromine goes on one side, the other bromine goes on the other, and that was a great fun reaction to study. Take benzene and react it with bromine. Well, you need a catalyst, and when you do, you get bromobenzene. In other words, alkenes have addition reactions with bromine. Benzene has a substitution reaction with bromine. And it's not just confined to benzene. There are substituted benzenes, and I'll touch on them in the next movie very, very briefly, and then we'll be seeing substituted benzenes, first of all when we make them in our discussion about the electrophilic aromatic substitution reactions. That's the subject of the next big series of slides, and of course we'll also see lots more substituted benzenes as we go through the rest of the course. But let's take one where we're thinking about a chlorine. Alkyl chlorides, what we studied in the last module. One of the big famous reactions, alkyl chlorides, react them up with hydroxide, can be a nice dilute solution of sodium hydroxide, and you'll substitute the Cl for the OH. Take chlorobenzene, and you think, well, this is just a good old RCl, right? There's a group attached to the Cl. React it up with sodium hydroxide, and you get no reaction. When you actually look at the thermodynamics of it, the bond energy of this carbon-chlorine bond is much stronger than the bond energy in any alkyl chlorides here, because this chlorine has p orbitals that have electrons in them that actually get involved in the delocalization of the ring here, which means that chlorine attached to a benzene doesn't behave like chlorine attached to a regular alkyl group. So benzene, very special molecule, not at all like you'd think it would be from the Kekulé structure. It has its own complete reactivity. That's why we call it, give it its own category of aromatic species. Now, in the rest of this little module, I'm going to talk very quickly about a couple of other aromatic compounds, just substituted benzenes that we've already mentioned, and then we will talk about the big reaction that benzene does do, electrophilic aromatic substitution, of which we saw a little taster here when we substituted a hydrogen for a bromine.